All right, let's dive into quantum mechanics. We're going deep with The Quantum Universe by Brian Cox and Jeff Forshaw.
Oh, yeah, this one is going to be fun.
It really is. So we're taking excerpts, trying to break them down so
Right.
that, you and I can understand them, and hopefully everyone listening can too. We're talking about the universe at the subatomic level.
Yeah, how it really works.
And it gets
the rule book.
wild, really wild.
Yeah, it's a place where particles can be in two places at the same time. Like, how is that even possible? It's wild.
Well, and uncertainty is a law, not just, a feeling
Right.
like it is in our big world.
And even empty space is, like, buzzing with activity.
It's crazy. And Cox and Forshaw, they get it,
Yeah.
They call quantum mechanics evocative,
Bewildering.
bewildering, and fascinating.
I'll follow those things.
It really is. But they also point out that even though it describes this world that seems totally alien to us,
Yeah.
it works.
Incredibly successful.
It explains how things actually work.
Like, astonishingly so.
Yeah. They even give this example of quantum electrodynamics.
Yeah, predicting, like, how an electron
Yeah.
behaves near a magnet.
Yeah.
And they're talking about, like, crazy precision.
Unbelievable.
It's like, if you could predict the distance
Wow.
between Manchester and New York
Yeah.
down to a few centimeters,
Oh, my goodness.
like, that's how accurate these predictions are.
It's incredible. But,
Yeah.
okay, if it's all about, these tiny particles we can't even see,
Right.
why should we care?
Because it's the foundation for pretty much everything.
Really?
I mean, think about it. Without quantum mechanics, we wouldn't have computers,
Oh, okay.
lasers,
Interesting.
and we wouldn't even really understand how stars work.
Huh.
So it really is the foundation for so much of our modern world.
Okay, so then how did scientists even, discover this hidden world, this world where things behave so differently from our everyday experience?
Well, it started with scientists realizing that, like, Newtonian physics,
Yeah.
the physics of Newton, couldn't explain some key things about atoms.
Like what?
Like, why don't electrons orbiting an atom's nucleus just constantly radiate energy and spiral inward?
Yeah, that always seemed kind of strange to me, even back in, high school
Right.
science class.
It doesn't make sense.
No.
And then there's the famous double-slit experiment,
Okay.
which really threw everyone for a loop.
What is that?
So imagine you're firing electrons one by one
Okay.
at a screen, and this screen has two slits in it.
Got it.
And you'd kind of expect, common sense would say that the electrons would go through one slit or the other,
Right.
creating these two distinct stripes on a detector behind the screen.
Yeah, that makes sense.
But that's not what
What
happens.
happened?
You get an interference pattern,
Like what?
like waves
Really?
spreading out and interfering with each other.
So wait, these individual electrons are creating a pattern like waves.
It's as if each electron is somehow interfering with itself.
How is that even possible? It's like one electron is going through both slits at the same time.
Well, that's where the concept of the electron wave comes in.
Okay.
But, and this is important, it's not like a physical wave, like a water wave.
Oh, okay.
It's more of a mathematical tool.
So a way of describing.
Yeah, the probability of finding the electron at a particular location.
So like a map.
Yeah.
Where higher peaks mean a greater chance of finding the electron there.
Exactly.
So the electron itself isn't spread out like a wave.
Right.
But its location is described by this probability wave.
Exactly.
So are we saying we can never know for sure where an electron is?
Pretty much.
Only the probability of finding it in a certain place.
Yeah, that's kind of the key shift in thinking here.
That's huge.
Yeah, we go from certainty to probability.
Wow.
It's not about where an electron is, but where it's likely to be.
That's a pretty big shift.
It is.
So how do physicists even begin to make sense of all of this?
Well, one of the key figures in understanding quantum mechanics was Richard Feynman.
Oh, yes, Feynman.
Brilliant guy, playful.
Yeah.
And he had this knack for making the complex seem understandable.
Okay.
Cox and Forshaw actually quote him as saying something like, subatomic particles don't behave like waves, they don't behave like particles, they don't behave like clouds or billiard balls or weights on springs or like anything you've ever seen.
That's so Feynman.
Right.
But, I mean, if even Feynman is saying that nobody really understands quantum mechanics, then how are we supposed to wrap our heads around it?
Well, Feynman was a master of using analogies.
Okay.
And to help visualize this whole particle behavior thing, he came up with this brilliant clock analogy.
Clock now. Okay, I'm intrigued. Tell me more about these clocks.
So imagine the entire universe
Okay.
filled with imaginary clocks,
Okay.
one at every point in space.
Gotcha.
And these clocks They don't tell time in the usual sense.
What do they do?
They represent the probability of finding an electron at that particular location.
Okay, so the size of the clock face tells us how likely we are to find the electron there. Bigger clock, higher chance.
Exactly. You got it. That's right. Bigger clock face means higher probability.
Okay, but how do these clocks actually work? Like, what makes them tick?
Well, so they have hands, right? And these
Yep.
hands, they wind.
They wind.
Yeah, based on the electron's journey. So as the electron moves, like let's say from point A to point B,
Right.
the hand on the clock at point A where it starts to rotate.
Okay.
And then the hand on the clock at point B, the destination,
Right.
it starts to unwind.
So one winds, one unwinds.
Exactly. And the amount of winding and unwinding depends on the electron's path.
Okay, I'm trying to picture this like sea of clocks all winding and unwinding as electrons are zipping around, but how does this help us understand anything?
Well, the key here is that to figure out the probability of finding an electron at a specific point,
Yeah.
you have to consider all the possible paths it could have taken to get there.
All the possible paths.
Yeah, so each path contributes a clock, right?
Okay.
You add up all those clocks, taking into account, their winding and unwinding.
So it's not just about the electron's final destination.
Yeah.
It's about every possible journey it could have taken.
Exactly.
That's wild, but wouldn't that be incredibly complex to calculate?
It is complex, but the math works out.
Okay.
And what's really cool is that sometimes
Yeah.
the hands from all these different paths, they align perfectly,
And six.
creating like a really high probability.
Oh, wow.
And then other times they cancel each other out,
Wow.
leading to a low probability.
So this is like the interference we were talking about
Exactly.
with the double slit experiment.
Right. It's this interference of probabilities represented by these clock hands
Yeah.
that helps explain these crazy patterns we see.
So the electron is taking all those paths simultaneously. I'm still trying to wrap my head around that.
Yeah, the interpretation can get a little tricky.
Yeah.
But the important takeaway here is that the math,
Okay.
using this clock analogy,
Mm-hmm.
accurately predicts the outcomes of experiments.
So Feynman's clock analogy, it helps us visualize this strange quantum world.
For sure.
But what about Heisenberg's uncertainty principle?
Oh, yeah.
Does this clock analogy help with that too?
It totally does.
Okay, good, because I remember that one being a real head scratcher.
Yeah, so Heisenberg's uncertainty principle.
It basically says that you can't know both the position and momentum of a particle.
Right, with perfect accuracy.
Right, at the same time.
Right, the more precisely you measure one,
Yeah.
the less you know about the other.
It's like the universe is playing hide and seek with information.
Exactly. And Feynman's clocks can actually show us why this is.
Okay, I'm listening.
So picture an electron moving along a straight line.
Okay, I got that.
We can represent its initial state
Yeah,
with a cluster of clocks.
a cluster.
Yeah, like a group of them, and the width of this cluster.
Okay.
It shows how uncertain we are about the electron's position.
So a narrow cluster means we have a good idea where the electron is, while a wide cluster means we're less certain
Yeah.
about its location.
Okay, now remember the clock hands wind as the electron moves, right?
Yeah.
So to predict the electron's future position,
Okay.
we basically use these clock rules.
Yeah.
We transport each clock to a future point
Got it.
and wind its hand based on the electron's journey.
So far, so good, but where does the uncertainty come in?
So here's the thing. If we start with a tightly packed cluster,
Okay.
meaning we know the electron's position pretty well,
Mm-hmm.
when we use these clock rules to predict its future,
Yeah.
the clocks spread out.
They spread out.
Yeah, and this spreading, it relates directly to the electron's momentum.
So a precise position leads to an uncertain momentum.
Bingo. And the reverse is true, too.
Oh, interesting.
If we start with a widely spread cluster,
Meaning we're less certain about the position.
right, the clocks will actually tend to cluster more tightly in the future.
And that gives us a more precise momentum.
Exactly.
So the more we try to pin down one, the fuzzier the other one becomes.
Yep. It's not about like limitations in our measurements.
So it's not like our instruments aren't good enough.
Right. It's a fundamental property of the quantum world.
Wow.
It's built into how these particles behave.
Well, I suppose it keeps things interesting. But we've been talking a lot about electrons as these, free-floating particles. What about electrons within atoms? Like I remember from chemistry
Yeah.
that electrons in atoms,
They're restricted.
they are
Yeah.
to specific energy levels.
You got it. And to understand why, we need to introduce another wave-related concept.
Oh, okay, hit me with it.
Standing waves.
Like waves on a guitar string.
Exactly.
Okay.
Standing waves are waves that basically seem to vibrate in place.
Right.
And the key thing about them is that they can only exist at specific frequencies.
Okay.
Think of a guitar string,
Yeah.
fixed at both ends.
Right.
It can only vibrate at certain frequencies.
Which produces certain notes. Okay, so you're saying electrons in atoms are like those standing waves on a guitar string.
In a way, yes.
Okay.
So an electron trapped in an atom,
Mm-hmm.
it behaves like a wave,
Okay.
confined to a specific region.
And just like the guitar string, the electron can only exist in certain standing wave patterns,
Precisely.
each corresponding to a specific energy level.
Exactly. And this is why
Oh, yeah.
atoms emit and absorb light at specific frequencies.
Right. Which creates those unique spectral lines that scientists use to identify different elements.
That's it.
It's like each element has its own light signature.
Pretty cool. Huh?
It really is. So these quantum concepts
Yeah?
that seem so abstract at first
What?
actually have real-world consequences.
Absolutely. Now, let's zoom out even further
Okay.
and look at how these quantum principles shape something we all recognize,
What's that?
the periodic table.
Wait, the periodic table? Something we learn in high school
I know, right?
is a result of quantum mechanics.
It is. It's amazing.
I never would have guessed that.
It turns out
Yeah.
that the periodic table,
Mm-hmm.
which was originally organized based on the chemical properties of elements,
Right, right.
is actually a reflection of the quantum rules governing electrons in atoms.
Oh, wow.
So each row
Yeah.
in the periodic table
Yeah.
corresponds to a particular energy level or shell in an atom.
So the periodic table is basically a quantum roadmap.
It really is.
Yeah.
And the number of elements in each row
Yeah.
is determined by how many electrons can fit in that shell.
Oh, okay. So why can't we just cram all the electrons into the lowest energy level?
Because of the Pauli exclusion principle.
The what?
The Pauli exclusion principle.
Okay, refresh my memory. What's that again?
So basically, this
Yeah.
principle states
Yeah.
that no two electrons in an atom
Okay.
can have the same set of quantum numbers.
Quantum numbers.
Yeah, think of it like each electron having a unique address in the atom.
Okay.
These numbers, they describe an electron's energy level,
Hmm.
angular momentum,
Got it.
orientation in space,
Yeah.
and its spin.
So the Pauli exclusion principle is like a cosmic zoning law.
I like that, yeah.
It's
Making sure that no two electrons have the same address.
Well, so every electron has its own unique spot in the atom.
Precisely.
And that has huge implications, right?
It really does, because without the Pauli exclusion principle,
Yeah.
all those electrons, they would just crowd into the lowest energy level,
Yeah.
and we wouldn't have the diversity of elements or the chemical reactions that make life possible.
Wow. So this seemingly simple rule
Yeah.
shapes the entire universe as we know it.
It does, but we've been really focused on electrons within atoms.
Right.
What about interactions between atoms?
Yeah, like how do particles actually talk to each other?
Well, that's where we go beyond particles and into the realm of fields.
Field.
Fields, it's kind of a leap,
Okay.
but it takes us to the heart of how the universe really works.
Fields. Okay. I think I'm ready for that leap. What are these fields?
So instead of thinking about like particles moving around in empty space,
Yeah.
imagine that the entire universe
Okay.
is like filled with these invisible fields.
Invisible fields. So like an invisible force field surrounding everything.
Not exactly a force field,
Okay.
more like a fundamental property of space itself.
Oh.
And each kind of particle, like an electron, proton, or a photon,
Yeah.
they all have their own field.
So there's an electron field, a proton field, a photon field, all like overlapping and coexisting throughout the universe?
Exactly. And here's the wild part.
Okay.
These fields aren't just sitting there.
So they're not static.
No. They're constantly fluctuating, like a restless sea.
Okay.
And it's these fluctuations
Yeah.
that can actually give rise to particles.
Wait, so you're saying particles just pop in and out of existence from these fields, like constantly?
That's exactly what's happening. Think of it like the fields are bubbling, and sometimes those bubbles turn into actual particles.
Okay, and then what?
And those particles can interact with each other through the exchange of other particles.
So it's not just particles moving around, they're also constantly appearing and disappearing, and they're like communicating with each other by exchanging other particles.
Yep. Pretty wild,
So
right?
it's like something out of a science fiction movie.
It might sound strange,
Yeah.
but this framework explains how forces actually work at the quantum level.
Okay, that makes sense, but
Remember when we were talking about potentials earlier?
right, like the potential that holds an electron in orbit around a proton in an atom.
Well, those potentials,
Yeah.
they're kind of a simplification.
Oh, okay.
Quantum field theory actually provides a much deeper explanation.
What do you mean?
Well, it says that instead of particles responding to some mysterious potential, They're actually interacting through these quantum fields
So how do they do that?
by exchanging particles.
So they're like sending little messages to each other.
Yeah, sort of. Can you give me an example of how this works? Okay, so let's consider the electromagnetic force.
Okay. The force responsible for everything from magnets to light.
Right, so in quantum electrodynamics,
Yeah.
the interaction between two charged particles, like two electrons,
Okay.
is described as the exchange of photons.
So when two electrons repel each other, they're like tossing photons back and forth.
Exactly. Like a game of quantum catch, right?
Right.
And these interactions can actually be visualized using Feynman diagrams.
Feynman diagrams, I think I've seen those before.
They're basically these little stick figure drawings showing particles interacting by exchanging other particles.
I remember thinking they were super complicated.
They can be, but they're a way to represent these super intricate quantum interactions.
Okay.
Each diagram shows like a different possible story.
Scary.
Yeah, about how the particles are interacting.
So we need to like consider all these possible stories to get the full picture.
We do. The quantum world is full of endless possibilities.
Wow.
And it's by adding up the contributions from all these possible interactions
Right.
that we can actually calculate the probability of a specific outcome.
So it's all about probabilities again.
It really is pretty amazing, right?
It really is. And to think that these quantum fields, they're the foundation for the forces that govern the entire universe.
They are. You mentioned earlier that this even affects things on like a cosmic scale, right?
Right. Cox and Forshaw talked about how quantum mechanics is crucial in the life and death of stars.
Yeah. So as a star starts running out of fuel,
Yeah.
it can't generate enough outward pressure
Right.
to fight against gravity,
Okay.
which can cause it to collapse.
Right. And that leads to things like white dwarfs and neutron stars. Right.
Exactly. And what's amazing
Yeah.
is that these incredibly dense objects,
Yeah.
they're actually prevented from collapsing further
Okay.
by a quantum phenomenon.
Really?
Yeah,
What is it? You're not going to say the Pauli exclusion principle, are you?
I am. It's the Pauli exclusion principle.
No, wait, the same principle that determines how electrons are arranged in atoms
The same, no.
is also responsible for holding up these massive stars.
It is. So in these extreme environments,
Uh-huh.
electrons or even neutrons,
Yeah.
they get packed so tightly together
Right.
that the Pauli exclusion principle just steps in.
And it's basically like, nope, you can't be in the same quantum state.
Right. And that creates outward pressure.
Oh, wow.
It's called degeneracy pressure.
So the Pauli exclusion principle creates like a quantum force field that keeps these stars from collapsing completely. It's another example of how quantum mechanics operates across such a vast range of scales.
Exactly.
Yeah.
From the tiniest particles to the largest stars.
Wow, this deep dive has been amazing.
It has.
We've gone from wave-particle duality
To the uncertainty principle.
PM fields.
Even the fate of stars.
It's incredible to think that quantum mechanics, even though it's so strange, is the key to understanding our universe at its most fundamental level.
It really shows how ingenious physicists have been in uncovering these principles
Yeah.
and just the power of human curiosity and exploring the universe's mysteries.
Absolutely. But even after all this, there's
Yeah.
still so much more to learn.
There is, for sure.
Here, the quantum world, it's just full of surprises.
It challenges everything we think we know.
And it keeps pushing the boundaries of our understanding.
Definitely.
It's a universe that is constantly evolving, full of endless possibilities and governed by rules that are both elegant and baffling.
So keep questioning, keep exploring.
And keep diving deep into the quantum universe.
There's always more to discover.
Absolutely.
Until next time.